My name is Dennis. I'm going to talk about this crazy script I wrote called Dr. Pebber. This whole talk is inspired by a broken piece of malware that I was sent. I'm not a reverse engineer. I'm a penetration tester. I mostly do web applications, but I like doing CTF stuff, and I really like radar. So the people at my company that do malware will sometimes send me neat things that they find. One of those people was working on a emotet sample. I'm told it's emotet. I don't know this stuff, but so I was told it's emotet. The typical way that we want to find the domains that it's calling out to in order to block it and to set up prevention systems and warnings and whatnot for our clients. The typical way that we would do this is we would detonate the sample and some automated process and then just see what comes out. However, this sample segfaulted very early. So he sent it to me to see what I could look at, trying to do a more static analysis approach. He even sent me what function he thought the domain decoding algorithm was in. So first of all, it segfaults in an address that looks like 0x012 and some junk, trying to write to that memory location when it's non-writable. That function that he sent me to look at was pretty straightforward, like pretty linear. There wasn't the graph was just one blob, so there was nothing really for me to think about, like, is this a decoding algorithm or what it is? And all the function calls in that looked like what we see here, where it's dereferencing that same memory address, memory area, and calling that pointer. The import table was also empty. So when you add all these things up, what it comes down to is an empty import table means that Windows isn't providing the Windows API to this sample. If the sample doesn't have the Windows API, it can't do really anything. So it needs to find the Windows API unless it's going to use syscalls, which I doubted. And these global functions would be a great place to store any Windows API functions it calls. So this malware is essentially in the same position that shellcode would be in. Windows shellcoders don't have the PE structure to allow them to have an import table. They also, Windows lacks a reliable syscall table. It changes between versions, so most of the time with shellcoders, they want to discover the Windows API in order to be version agnostic for their shellcode to work in more situations. The way that shellcoders do this, and the way that this malware was doing this, is by parsing the process environment block. The process environment block is found at fs, dereference fs plus 0x30. The thread environment block is actually a pointer to the thread environment block for a Windows process, and 32-bit is held in the FS register. 30 bytes into it is the pointer to the PEB, so if you dereference that, you get to the PEB structure. If you go 0xc bytes into that, then you get another structure, and you keep walking down. We're going to, in a little bit, I'll show you a demo that actually goes through the malware as it's doing this. And there's a couple key aspects that make it easier to identify, but we'll get to that when we see the malware. Typically what happens, like with Metasploit Shellcode, there is you inevitably come down to finding the names of the WinAPI function calls that you want, and you hash them and do a hash compare. Usually you do the hash compare in shellcode because you want your shellcode to be as small as possible. If you have multiple functions that you're looking up, then the hash of the name can save you space. In this case with emotet, the author just wanted to be a jerk and make me reverse a hashing algorithm. So given this sample, given that it doesn't run, I was trying to think of what options I have available in order to try and reverse this efficiently. Static analysis, I would essentially read the hashing algorithm, which isn't very complicated. It's not really hard to reverse, but it also wouldn't, I believe I saw in there where certain values were easily changed. The hashing value could change, the hashing algorithm would change, so it wouldn't live past that sample most likely. And it's just not fun. It's, I've reversed hashing algorithms before, and it wasn't like a good hashing algorithm, it's just multiplying, so that's not neat. So I don't want to do that. I want to sneak some fun into work somehow. So dynamic analysis, I can't really do dynamic analysis because it crashes as soon as it finds the first function that it discovers. It tries to write to that global memory space, which is non-writable, and it crashes. If I knew more about Windows, maybe I could make that memory space writable. Really, this is the way that I should have done it if I wanted to actually get my job done quickly. I didn't think about it at the time because I was stuck in Easel mode, which is the choice I took, as we'll see. But I could have just knopped the instruction that writes to the non-writable address space and then set a breakpoint there, and then continue through the code, hitting that breakpoint. Every time you hit a breakpoint, you see where the when API function was used. Once you get the when API functions, then you can use radar to cross-reference them, and from cross-referencing, then you can work backwards to find the domain decoding algorithm and get a head start on things. So what I did go with, of course, was Easel Emulation. This is an interesting place to be in. The binary doesn't have str compare, it doesn't have access, it doesn't have any of these functions that Easel would choke on. So the things that that would stop you from running Easel are kind of out of the mix, with the exception of the Windows structures. The algorithm is essentially just parsing raw binary data, the Peb and its associated structures as you walk down. Easel can do that if it has the Peb and the associated structures. And I thought it would be much more fun to learn about Windows and those structures and get more in-depth into it, and to create a, by recreating a fake version of those structures in a minimized format that could be injected into Radar's cached memory. And then you can just let Easel run through the hashing algorithm itself and give you the answers for you. So here we have the sample. It's a PE 32-bit executable. First I'll show you can you guys see my terminal okay? Is that big enough? Okay. Yell at me if I need to make it bigger or smaller or something. So if you just run the Dr. Pebber script, it will print like an annotated structure, which is great if you want to learn how this stuff looks. This is the raw hex dump is what is actually being shoved into Radar's memory. So open the malware in Radar. I did modify the malware because I'm paranoid. I just wrote Fs at some point down here. I have a little script that builds that binary file, enables IO cache, also does the analysis stuff for me just for the sake of this talk, and then lets me know that the fake Peb was loaded into offset 0x30. This is where we'll see there's a access to the FS register, and by default, I guess Easel uses 0x30. I guess FS holds 0 by default, so I'm just leaving it that way. It doesn't. This address, the injected fake Peb and various structures only get to there, which doesn't clash with any of the malware code that we're going to run. I don't think it clashes with any of the malware code, so it won't it's not too important that we're picky about where our code goes. Doing that also initialized the Easel stuff, so we can see the registers up here. This is the entry point. We know the malware can't really do anything without the Windows API. It can't access the file system. It can't connect to the internet. It can't do anything that we would want a computer to do. It has to ask Windows, the kernel, for something. So the algorithm to find how to ask the Windows kernel for something must be close to the beginning. So S just steps through. Here's the first function call. This is why ESIL was on my brain. Usually, like for crackmes, you'll quite often see a big chunk of push instructions in order to build a second stage payload, which then means I probably want to grab that data once it's been put onto the stack. And my previous attempts were using radar was essentially like PDF and then pipe that into like a sort command and then sed some trickiness to try and just get these last value out. But I realized that if the malware guy's a real jerk, then he could put multiple instances of the same push or in various orders or rewrite something that he'd already written, and then I'd end up with bad data. So instead of that, one of the nice things that you can do with ESIL is we can just continue our step until we get to this first function call. Now all those pushes have been done. All of that information is in the stack, and radar with PCP, I think, at ESP. So the ESP stack pointer, ESIL has it in the right spot. All of the pushes are below that, so we can do that and get the raw data just as it appears on the stack. It turns out this is not what I originally thought it was. This isn't like a second stage payload or anything. This is a hash table. Each of these values corresponds to a hash that'll be used to associate it to a desired Windows API function call. So the first instruction, or the first call function here, we can quickly see that if the call fails, then it jumps to the exit, so that's bad, so we want the call to return something. If we go to that call function, we also quickly see FS, so the FS register is being used. If we step through it, we see that FS30 being moved to EAX puts 0x34 into EAX. We already loaded our fake PEB into memory, so if we seek to EAX, we can see here the Dr. Peb is what I used for to distinguish that this is part of the ESIL or the Peb stuff that I loaded into memory, and it's the inherit address space member of the Peb. So now we can step through this, and without a Windows virtual machine or anything, we can actually see the code being decoded, the algorithm working. It's not the most fun. If you look at the graph view, you can quickly get some aspect of what's going on. There is a big outer loop here. There's an early exit here, so this is probably the bad end. A big outer loop on the outside. That's probably, if you know a little bit about how the Peb works, eventually you get to load modules, which are corresponding to every DLL that's loaded into the file. Even though the import table is empty, there are by default kernel32 and ntd.dll, whatever it is, are automatically loaded. The kernel module list is a double linked list in 3 different ways that you would probably want to loop over to find the correct DLL file. So that's what the outer loop is. The inner loop here is the hashing algorithm. If you go to So that's the hashes the name of the DLL file. Then here it checks to see if it matches a variable. If it does, we get to the good end. So AE continue until $signs. Let's Easel do all the heavy lifting, and hopefully when we get to the ret instruction, I think I went too far. So we returned, EAX holds what the return value was, which is 0xD0, which if this was a normal Windows install, then that would be bad. But if we go to 0xD0, we see that it is the image DOS header, or the base for ntdll.dll. So Easel correctly recreated the hashing algorithm just by having this binary blob in memory, such that it correctly discovered that the malware sample was finding ntd.dll.dll. We go back. The next function call is more tricky. If we look at the, it's not as bad. And again, if you reason about things, we already have the DLL, so we need to walk down the DLL's information until we find the function names, and then we would probably want to loop over those function names. That's this big outer loop. Then this loop, this tiny loop here, is obviously the hashing algorithm, the I multiply here. And we can continue until there, AE continue until to verify. We see EDX as SHA-1 final. That's the first name. That's the first function name inside of ntd.dll. So this is looping over that function name in order to create a hash. The good stuff is, once the hash is created, it loops over the hash table to see if it's a member of the hash table. If it's not, then it continues on. If it is a member of a hash table, it eventually comes to this piece of code here, which is where this line is what was crashing the value. We can AE continue until, so run Easel until you reach this spot. This takes a while because it's iterating over all the functions that are in there until it finds the first function that's used by the malware. So while it does that, we'll skip to the potential uses. I don't do malware analysis, so I don't know if this is cool or really stupid. It turned out to be, it wasn't the best way to do this. It was a neat way to do it, and it was a neat application of Easel. So I'm hoping that presenting it to you guys allows you guys to consider better uses of Easel, maybe with this, maybe with something else. So the annotated output is a great way of learning those structures or debugging your own shellcode if you're creating it. This doesn't work with shellcode right now. I created the binary blob based off of reversing this emotet sample, which hashes the loader module names, which most shellcode doesn't do. Most shellcode relies on the fact that the order of those modules is pretty static across all versions of Windows. So they just grab the third version to get kernel 32. So it's off a little bit for now, but it's actually a really easy fix. And you just throw another kernel module in there, and it all lines up appropriately depending on which direction which of the double linked lists you take. And from that, you can quickly reverse shellcode or try and debug your shellcode in Radar 2 without even using a file or a C harness or something like that to get it executing. My intention, my hope was to automate this process completely so that I could just do it with R2 and Docker and essentially execute until Easel reaches a memory location that is inside of the Dr. Pebber binary blob. All the functions do map, all the function base addresses, function base address do map to a spot in that binary blob that's just a single byte return. So if you told Easel to break once you hit there, then that would imply that the malware has decoded everything already, and you can grab memory and see what's changed in order to find what functions are being used. We wrote all the functions in memory, so like if we get the pointer table, then we know where each function is from that pointer table. It's also kind of neat because the OS isn't being used. If the being debugged flag is messing with you, or if the isDebugger present call ends up being used, then you can rewrite the isDebugger function call with a quick bit of assembly that will just return the isDebugged flag from the Peb. That flag does exist in the Peb and can be rewritten. So then any modification by the malware to try and check if the debugger is present or if isDebugger present is being hooked can be bypassed. The biggest drawback to it is it's slow. So it did finish. Oops. We can see ECX is being moved to that memory location. ECX is held here. So if I seek to ECX, that's the return for NT unmap view of section. So the very first function call that's discovered is NT unmap view of section, and we can see where it falls in the array by checking ESI, which is 1C. Yeah, thank you. So 1C. So it's the 1C element of the array. You can run it again, and it doesn't take a really long time, but it does take a little bit. And that's the biggest drawback to this, is that it's much faster to run it in there it went. That was just for one iteration to find the very next function. There's a lot of functions. So trying to run until return takes quite a bit of time. Also, the second biggest problem with it is that I wrote it, and I'm not that great at object-oriented stuff or at this type of development. So if you find any problems with it, if you actually want to use it and you find some problems with it, let me know, or you can fork the project and steal it and do whatever you want with it. It's currently 32-bit only, and also this is pretty easy to detect. If for some reason Emotet developers thought that they wanted to stop Dennis, then they could just check the distance between various sections and see that the Peb is far too close. The tab is right next to the Peb. Structures have been removed from it, and so that's not valid, and it can kill itself early. Also, lazy loading API calls, so it would load the first call that it needs only when it needs it, and then it can use that function call, which would break Easel, before we found the second function call that was discovered. Okay, that was my talk. I hope you guys enjoyed it. Do you guys have any questions? Thank you. So.
Any question?
Yes. Here in front.
Was it very difficult to find out about all the Windows structs in the PEB?
Yeah, so I don't think that this stuff is actually undocumented, but I really hate Windows. And and that's actually a great deal of my motivation was just I don't want to start another Windows VM and click through the debugger and all that kind of stuff. I'm not very good at Windows, so that was a lot of the motivation was I wanted to learn more about this stuff. Like the debugger flag as part of the PEB, which I think is essentially, is debugger present, the WinAPI function call. I believe that just returns that value from the PEB. So like those kinds of interactions, I was interested in learning to find more about this stuff, which was most of the excuse for doing it. Also to learn more about Easel, because Easel's awesome. But also because I just don't like Windows, and I want to have fun. I don't want to start a Windows VM. That's not fun. So Easel's much more fun. Was that good? Yeah. Cool. Any other questions?
Nope.
I can't really see.
Okay. Thank you.
Good. Thank you.